Okay, so last time in class, somebody asked a very valid question, and it's not an easy one. So basically, just look at it, okay, and then you can kind of make a decision. So basically, somebody said that for the shear, when we use this relation, is it a sign convention? Okay, and my answer was like, yes. Generally, you will specify because the shear is really a 3D effect. So let's say shear is a 3D effect. Okay, so generally what you would do, it depends. It doesn't matter which what you choose as direction, as long as you are consistent with all your cases. Because in real life, you agree that it should not matter if you have, let's say, a structure, and if you twist it on one side and the other side, there is not really tension, compression, and shear. No, shear is shear. All right. But I tell you, sometimes what you need to do is you need to make a decision, and let's say this could be your definition for shear, but this will be shear so this over here is the shear due to a shear force V. Okay, so imagine that you have a problem just like the one we did the other day, and let's say you have here a beam, whatever. I'm just going to do half of it this time. And you want to know what's happening here. So what you need to do a little figure, right? And make a sketch about to see what would be the shear if it was coming in this direction, no? Obviously, if it's coming in this direction, it's going to produce a different shear than if it comes in this direction. Does that make sense or no? Okay, and same thing if it comes up and bottom, no? All right. But since you had that question, that made me think about it. Okay, what else can cause a shear? The main thing that can really cause a shear is a moment or a torque, no? Okay, so I'm sure you have studied that equation. So let's look at it now. What is the shear caused by a torque slash moment? So let me just do a figure. You know, I like figures. So you have a circular torque. Let's say here is fixed at this end. And then I don't know how you like to plot moments or torques. You can either do this, or sometimes in book, what do? They kind of do like a double arrow, no? For moments and force. I don't know which one you want to use. I don't care. So basically, I'm sure you have studied this. In this case, the shear stress is given by what? T times R IP. Some books use IP, some books use J, okay? Personally, I like J, but I know most of the books use for I. I stands for what? I, polar moment of inertia, okay? Area moment of inertia. Okay, where let's say here, where J, IP is the polar moment of inertia. Okay, in most cases, J is equal to pi over 2 outside, let's say, radius to the power 4 minus r inside to the 4. If your cross section is of this shape, okay, so it would be r outside, r inside. Okay, and something you have probably studied as well from solid mechanics, that when you have this, you can also have the angle of twist. Generally is given to you under this form in different textbooks. This is the real equation, okay? That's the one is really the correct. But the one that Johnny used is, or once you do the integration throughout the whole length of the beam, this is PL over GJ. This would be the angle of twist. So why did I decide to do all this stuff today? So in here, for example, if you have, I mean, I put a circular one, but it doesn't have to be the circular one. But let's say I put a torque over here, T, in that direction. In what direction would be the internal shear? It should go on the opposite direction, no? In order to be opposite. So you see, in this case, let's do the same arrow as before. This will be your tau now. Does that make sense? The shear here should counter-react the external force, no? If you think about it, summation of external forces needs to be equal to the action of the internal forces, so that is equal to 0. Okay, so it would be equal to 0. All right, so now, because of this equation over here that you see over here, let me square it here. All right, so what should be, if we look at this equation here, what should be the distribution of the shear? Is in function of what? T would be a constant, J would be a constant, would be in function of the radius. So let's say that the distribution of the shear would be, we need to do the one way, would be this way, no? All right? All right? Okay, why am I doing, I'm not expecting you to know the answer, but why am I doing here all the time circular stuff? Instead, I could put something square or rectangular and we could have shear as well, no? Okay, so if you want, here I'm just gonna put it on the next page, but. Because the radius is constant, like the maximum radius. I think you're on the right direction. What happened is that J or IP is really known just for a circular cross section. So for example, here if you have this, you have the J exact. But if you have any other type of cross section, okay, and can be also the I-beam, etc., the J is just an approximation. And in most cases, what they do, okay, is that you are trying to, and what is the main reason? It's because we just say that if you have here a moment applied to this, you're gonna have inside a, on the opposite direction, shear, no? Okay? What's gonna happen is something that is not circular. What's gonna happen at the corners? Do you think the shear is gonna be constant? Probably at the corners is gonna be some type of concentration, no? Of stresses. Does that make sense? So the J is not exact, okay? And generally, this is approximate either by one that will have the same area or something like that, you see, by different ones, okay? Actually, this one is approximated by one of different thickness, okay? But we can do that. I don't want any too much information. So yes, let's do it now. Why not? So if you look at this equation, then what is beneficial for you to have the area? At the center or the outside? At the outside. So if you look at it, if you think about stress, if you just think about stress, shear stress, to be specific. So for example, this would be really good, no? Yes, because you will have your area on the outside, no? Yeah, because what do we say about the distribution? Is that it will be 0 over here and it will be maximum at the top. So this is a tube instead of, let's say, a shaft. All right. Now, let's go back to what we have learned. So really the tube is what? To the normal stress. What was the best cross section for the main? Normal stress, not the best, but let's say for the, but here bending. Better than normal because it's really bending. Where was the maximum stress all the time for bending? What was the expression? Sigma equal my. So if you think about it, where was the maximum stress? Again, so it would be the top and the bottom, no? So if you think about it, the tube is the same thing as the I section that we have for bending, no? Yeah, you need to put the area where you need it. But now what would be the issue? So a tube, I'm not going to write it down, really would be better to resist shear. Okay? But will it be better for the angle of twist? No, I mean, probably if you have something solid, it's going to deform less than a tube, no? You need to use your head, okay? So that's one problem. For example, here they had for a couple of years over the Baja team is that they were doing the design of the transmission shaft based on stress. And if you do it based on stress, then what can you do? You could say you could use a tube, no? Yeah. But then what happened with the angle of twist? So correct, it's twist, so they have slippage on the gears, no? Because it will be fixed, the tube will twist and the gears will not connect. So by general rule, if you design a shaft, you need to go with what? With a solid shaft, no? Don't go with the tube. All right, even though you do the design based on shear, a tube will be more than perfect. Okay, it will actually be better almost than the shaft in many cases. Okay, I mean, it would not be better than the shaft, but it will be at least equal. It will be equal in resistant stress, but it will be lighter than the full solid shaft. Okay, doing all this stuff. So now, really, what I wanted to do is this. So can you add together the shear stresses due to, let's say, bending, let's say Vx dy, and due to torque. So let's see. Let's do a circular, okay? I don't know exactly how it's going to be the circular. But what is the problem where this is due to Vx, so let's say to Vx or Vy? What should be the distribution? What should be the shear on the outside? This is due to V and to V now, not to torque. What should be the shear at the top if we only have Vy? Didn't you just do an assignment? What should be the shear on the outside? 0, no? Okay. And what would be the shear maximum? Right in the middle. So let's say that we have something like this. I'm going to make it here. So will be here is 0. Here we should be 0. And let's say in the middle should be max. So I don't know exactly how it would be on a circle, so I'm going to make it up. But let's say it would be something like this, okay? I don't guarantee this one. So this is due to V and Vy. Now, if we have, let's say, the same cross-section, and now this one is subjected to a torque, T. What would be the shear distribution? I mean, we just did it. It should be maximum on the outside. So, can you add them together? The answer is yes. But does it make sense to add the two maximum values? Maximum value due to the shear forces will be where? In the middle of the cross section. And if you do the one due to torque, it will be where? Right on the outside. So if you do the addition, you need to be careful about the location, no? Yes? Does that make sense or no? So the answer is yes. They can be added, but the location is very important. Okay, so you cannot go and just add them together. All right, like, okay, I do this and that's it. Any question about this? This is a lot more conceptual. Does everything make sense? Yeah, I mean, structure is nothing complicated. You need to use your common sense. Structures, like I said before, there is no complicated math. It's add, subtract, divide, multiply. All right, but you need to have an understanding of what is happening. No, you need to know what is a normal stress, what is the tangent stress, and what is the distribution of the stresses, basically. I mean, let's get an example. Let's say somebody asks you to say, what is the maximum stress on the outside? Yeah? What is the maximum stress on the outside? Can you add these two terms together? You can add them together, but then the solution will only be this one because it's 0, no? Over here. So what happens if you add the magnitudes? If you don't pay attention to the distribution of the stress? It will make no sense, no? So for example, you need to say, okay, where am I doing the addition? The location is important. So if you do it in the middle, will this one be important? It will be 0. So if you go somewhere in the middle, it will be some portion of each one, no? That's what I'm saying. Does that make sense? Okay. All right, so let's do here an example. I don't know if we have time to finish it today. Let me know, guys, because I don't have a watch. I don't see the time. Oh, I can see the time on the computer. All right, so let's see this problem here. In this problem, there is a post, if you want. That is fixed to the ground. Now, to this post, they are welded or attached to all the tubes. Okay, let me give here the dimensions of the tube. So all the tubes are the same. So let's say this will be it doesn't matter what that is. I just want to put here the outside diameter is 9 inches. Inside diameter would be 8 inches. Now I'm going to give you, so the forces over here, let me first give you the forces. There will be a force here of £3,600. One here going down was 14,000 pounds. Here would be another one of 3,000 pounds. And here there is one of 2,500 pounds. Okay, so let's select here some type of coordinate system. Let's say this is our Y. The one along this line over here will be the X, and the one along this one will be, let's say, the Z. Okay, I'm gonna make it a bit faster here. This is point A. This will be point B over here. This will be point C. And here will be point H.
C at the force application, or is it at the?
Oh, sorry, C is over here. Thank you. Okay. So instead of doing a bunch of measurements here, let me just give you the location. All right. So let's say that here we have position of point A is in that coordinate system is, let's say, will be 0 on the X. That should be point B. No? 11 5. I will check it now. Okay. R sub B. R sub B. Okay. Let me look at this. Let's see. If I look at the figure, should be 5 on the Z, on the Y, 0 on the X. Okay. Now, point B should be then just, oh, I don't have the dimension on this figure. Okay, might not be needed. Let's keep going here. So will be, it's just on the Y, so 0x. Here, I don't know it now, okay? I don't think we need it, that's why. I don't have it on this figure. Okay, what I'm looking is at this figure. Or I'm not lying to you, I'm just looking at this problem. Looks like I forgot to put that measurement. Okay, and C is not a number, it's a question mark. Yeah, because I don't have it on the figure. So it's probably because it's not needed. If we need to put a value, we'll put it. And R sub C will be located at 8. X and 0. Okay, if you want, let me try to put some number. I didn't want to do this, but otherwise it would not be a good example because it would not with it. So let's say it will be 8 feet. The height over here is 6 feet. This arm over here is 5 feet. This is what I have. And this height over here is 11 feet. Okay. So we need to put a value for B, we'll put it later on, but for now, it's not important. So obviously this looks pretty complicated, no? Okay. So the thing is to be methodical, all right? Because at the end, what's going to happen? You agree that here, what is the most critical point where we need to calculate the stresses? Where is this going to break? If it's going to break somewhere? Probably here, no? So that's why in this problem, they ask us to determine the stresses at point H, okay? Because it's the most critical. Maybe they can ask you to find the stresses at the connection of each one of the bars, no? To know if they're going to break. But let's just do that. Okay, so we know that the tube over here will be subjected to what at point H? The loads will be what? We have some shear forces, no? Acting on it. But now all these forces acting over here that will become shear will be also creating what? Moments. So yes, you could do this like you were doing in statics. You could do one, taking dimension and see the moments. All right. But since there are so many forces, what I like to do is just follow a procedure, no? Okay. So let's first do using vectors. So let's say if we use vectors, that would be easier. What would be the vector at point A? Would be what? 0 on the X and negative 2500 on the Y. FB will be what? negative 14,000 only on the Y. Okay, now the one that is more complicated, F sub C, will be equal to what? 0 on the X, 3,600 on the Y, and 3,000 on the Z, no? Okay, next, what is the definition of moment? What is the equation to determine the moment? Force time distance, that's good, but if you do the 3D, it would be what? Perfect, R cross F. Okay, and remember here, we're trying to find the what? Moments at which point? At point H, perfect, so I'll just put it there. So I'm gonna do one by one, but then what would be the moment created by the force A? How do you do the cross product? You have IJK of what? R sub A would be equal to what? So 0, 11, 5. You see, you don't have to worry. And what is F sub A? 0, negative 2,500, 0. So this will give you what? If you do the cross product, this will be equal to what? 11 times 0 minus 2,500 times 5. Okay? And that will be just one component on the X. So this will just give you 12,500 on the X. What will be the other components on the Y and Z? You know how to do the cross product, no? If not, let me know and we do it once together. It's negative, negative. All right, so this will be what? And here we're gonna have to be careful because what are the units here? Okay, let's be careful because we have to change that at the end. This will be LB per foot. Okay, let's do the same thing for MB. MB this time will be equal to what? IJK. And let's see if the math gives us the right thing. So this should be what? Okay, we don't know the value, so let's say 0, question mark, 0. Maybe I can put a value, but and then what is FB? 0. I know why now there is no value. Because, I mean, without looking at this, just look at the figure. Would this force be creating moment about point H? No. So no matter what this value you put over here, you're gonna have 0, no? Okay. So that may be why they did not put a value on this problem. But maybe we can put it, okay? You want us to put a value? It simplifies or
Well, it points out that like borrowing points out the fact that.
all right, that's what I'm saying. Okay, that's why I put it. I mean, it wasn't on the problem, okay, on the page I copied, so that's why I did not put it. Okay, but it's 0. I mean, you don't need to do this to see that it's 0. Okay, so the math should tell you what your intuition is telling you. No, that's the way to check the problem. And finally, so this one's a bit more complicated. Obviously, is MC, where we do exactly the same thing, will be equal to what? IJK. What is R sub C? We had 8, 6, and 0. And now the forces for S sub C, we had 3,600 on the, 3,600 on the Y, and 3,000 on the Z. Yes, because yes is a 0, sorry. So here, let's do the first one, the math. So what do? We cross this one, you do 6 times 3,000. That would be 18,000 minus 3,600 times 0. Now the second term would be what? Remember, it should be plus, minus, plus, not the cross product. So there's a minus in front. This one, we cross this one. What do we have? 8 times 3 should be 24,000, but don't forget it should be a minus in front. So minus 24,000. And now the last one, you cross this one, should be 8 times 3,600, which is 24 plus another 3, 28. Let me look at it. I have it here, 28,800. And this should be pound per foot. Okay, so here we did the moments. Now let's look at the forces. And I know we have them, but let's just look here. Forces. Forces. We don't need to put acting at point H. So what do we have? We're gonna have F is gonna be equal to S sub A plus F sub B plus S sub C. So this will be equal to what? Let's see. So I'm just copying what I did before. 0 minus 2,500. 0 plus 0 minus 14,000 plus 0, 3,600. 3,000. So that's going to give you that the total force will be equal to what? 0 minus 12,100 and 3,000. Okay, and now let's do the moments. Maybe I should have done that before, but we can do it now. So the sum of the moments will be M equal to M sub A plus M sub B plus M sub C, which is, we just had before, M sub A was equal to 12,500. What was MB? 0 plus 18,000 minus 24,000, 28,800. So this is going to give you that M is equal to what? $30,500 minus 24,000 and 28,800. This would be pounds per foot, the pound force. Okay, so I think this section here, the next one, this section and the next thing we're gonna draw a sketch is the most difficult of this problem. Okay, and we just kind of follow procedure. So basically what I'm trying to do is what? Loads at point H. So that means forces and moments acting at point H, no? But I don't know if I'm going to do one or two figures. 1 might be too much, but H is in the middle of the cross section where is underground, no? All right, let's say it's in the middle. So let's say if I do here a figure, that's going to be the best way to do a figure over here. I want to do 2 just because I'm scared to put too much information in one. Actually, you could have done that through the top instead of the bottom. Do this through the top, that'd be easier. And let's say this is our point H. Okay, and let's recall our current system. We had Y, X, and Z. Okay, so if we look at the figures, if we look at the data and the figure, let's see if I can. Okay, so do we have anything on the X? No, it's 0. Do we have something on the Y? Okay, so what does that indicate? If I just do on the shear forces, if you think this way, that means that we have here shear force, let's say, Py equal to what? 12,900. If you want, you can put a negative sign, you can make it up and put a negative sign, or just make it down, showing that it's going down, no? All right. Okay, and then what else do we have? Okay, we're gonna have another on the Z, and this one will be equal to what? Okay, so let's say here we have here, I shall learn from the middle, will be DZ equals 3,000. Okay, so what does that mean? Due to these forces, what are you gonna have? I didn't calculate the reactions, but yes, you have reaction, but now think about stresses. What type of stresses this will produce? This produces shear stresses, no? Tau equal VQ over IT, no? Yeah? So from this one, we're gonna get what? Shear stresses, VQ over IT. I don't know if you can see that. Yeah. So this produces shear. Now, what are we also gonna have over here? We're gonna have here Y, X, and Z for moments. So let's see, what do we have? We have a moment. Do we have a moment on the X? Is it positive or negative? So that means it goes what? Clockwise or counterclockwise? Counterclockwise, and we have here X would be equal to what? 30,500. In here? Yes, it's the point H where we need to do the calculation. Okay. Now, what is My? It's negative, so that means counterclockwise or clockwise? So we can put it here clockwise then and say My equal to what? 24,000. 24,000? I don't know why I was going to put it 500. Sorry for that, 24,000. That's what I'm looking here. Which one? Yes, 18,000. No, it's good. 30,500. This is 18,000. Okay, so now we have this. So now we need to be careful here. And then what else do we have? MZ, is it positive or negative? Right, so it will go counterclockwise. So MZ equal to 28,800. Okay, so now what's important here is to recognize what? I mean, you don't have to do that if you want one, but really My is what? What type of load is My? It would be about the cross section, really would be like a torque, no? What My is going to produce what type of loading? I mean, shear, no? The twist, I remember it would be shear stress. And what would be the equation we have to use over here? TR over J, no? Due to T. And what about MX and MZ? We produce what type of stress of the formation? It will produce bending, no? Correct? So this produced for the equation M, whatever, Y or Z over I, no? So do you understand how to find the loading? This is what I think the most difficult part in engineering is to find the right loading at a point. Because you can be the best one using the equations. If you have the wrong loading, whatever you're gonna get is wrong, no? Okay. You saw that here instead of, I mean, you could take here, start taking moments over here about each one of the forces that you would do in statics. You can do it that way, okay? But I think this way, which is the mathematic way, it makes it easier. All right. So, any question about how we got here? To me, this is the problem. How we got here and which load and what type of stress each one of the loading is going to create. Is that clear over here, this figure? Yeah? Okay, so from now on, it's just logging numbers, use the equations. That's it. The difficult part is here. All right, so now we can start going. So next thing we need to do probably is to find the cross-section properties, I'm guessing. Okay, I don't know if I have all the values, but okay, you might have to help me here with values. I don't know if I have them all. Okay, you help me with the values. That way we do it from scratch. So first thing I'm going to look is at cross section. Properties. Oh, actually, we have one force here, which is going to create. You see, I forgot something here. Be careful here, guys, because you see, I wasn't looking at it. Here, this is going to create shear, but this force is not going to create what? This one comes straight into the axle, so it's going to produce normal stress P over A, no?
Now, if you were to look for normal stress in this problem, would you also have to factor in the 14th element?
Yes, that's the one I'm putting here. This is the P over here. So let's see, we're going to put it on the 14,000. Yes. That's what I was trying to write over here. Okay. But let's go one step at a time. I don't know. I mean, I don't want to change the figure now. We go back. So cross-section property. So the first thing we're going to look at it is at point H. At H, let's add over here at H. So it's clear. So let's see, we have here. All right, so the good thing about this is going to simplify everything. All right, so the first thing, and help me with the values because I don't have the values. What would be the area? by a square, or we have the diameter, so we're using function diameter. What this would be equal to what? By d squared over 4, no? So we know here the outside was what? 9, if I remember. Oh, we need to be careful here. And the inside is 8 inches. So we're gonna have to be careful with the units once we apply the loads. So this will mean that A will be equal to pi over 4 d outside square minus d inside square. Can somebody give me that value, please? I have some of the results, but I don't have everything, okay? $13.35. What? Yeah. Well, give me 4. Doesn't matter. Okay, that's fine. Okay, and now we're gonna do the moments of inertia. So okay, and I, the moment of inertia, I'll give you the expression. It doesn't matter here about x, y, because everything is circular, no? So it should be the same. So it should be I is equal, I give you the expression, is pi over 64 the outside, but this time to the 4 minus the inside to the 4. So if you can give me a value, that would be great. One-to-one? Just one-to-one? Okay. Okay, just to be big, okay? Okay, now the good thing, keep that value. J, if you do it in function of the diameter, is equal to pi over 32 d to the outside to the power 4, d to the inside to the power 4. So, okay, so just like I said today, the idea is to finish up this problem. So we started this problem, and here we have all these loads. And I tell you, the most difficult part of this part, generally, is to find what is the loading at the point of the cross section. They ask us to find the load. So in this case, they ask us to find here at point H. All right. The original point is at the edge of point H, but I think this one we say point H was in the middle. So the procedure was to find the position vector of each one of these points, A, B, and C. Okay, and it's defined here by R sub A, R sub B, R sub C. Now that we know the position vector and we know the value of the forces at each one of the points, we can define what is the moment by just using the moment equation, which is M cross R cross F. Okay, so we did that for each one of the forces, and basically this is what we got over here. So after doing the forces, let's look at this figure here. So we have this figure over here. All right. Does it better with light or no light? Is that better or worse? So the no light? Is that better? Yeah. Okay. So I can zoom in a little bit as well if you want. You're welcome. Okay. So basically, I think this is where we stop. At least that is the last page I have. I think we did one more step, no? Okay, but let's take it from here because I think I did one mistake. So I want to just take it from here. Okay. So I just want to look at the log because I think I started to go too fast last time. So we have this. Let's see if you can see this. Yes. All right. So what we're going to say first is that we need to define what would be the axial stresses. All right. And That's the last thing we wrote, or
Yeah, that was the last.
okay, so I might need your help over here. So the axial stress. So the expression for the axial stress, probably I can redefine it. So, okay, so for the axial stress, I think the axial stress for us would be on the Z, since we have not on the Y, will be equal to what? We have moments in so we have here, we're gonna have then we have the forces. Okay, so the general equation I think is P over A. Okay, plus mx, I call this one C like I did last time, over I sub x, plus mz C over I sub Z. Okay, and in this figure here, we say that I'm just copying that from last time. This C over here is actually Z, and this one would be actually X. All right, and we add here the figure. Let me just redo the figure over here. Of the cross section. So we have here wait, this is, let's say, the Y. YZ. And what did we say we had? If I look here at the forces, all right, I'm looking here at the forces, all right. So what would that mean? We have over here a 12,900. I think that's not on the original figure. Then we're gonna have what on the Z? We have here a 3,000. But the most important here is the moments. We had a moment here. MX, so I'm looking all this from the figure here. 30,500. And the other one is about the Z. Is 28,800. Okay, so last time I think I was rushing it because I started to look at the other figure instead of this one. In this case, what is the value of P? I think last time I put 14,000, no? But it's not 14,000, it's the 12,900, no? Yes, because I look at the first figure. I think last time I couldn't find that page. So I look at this figure and saw this one right away. I didn't pay attention about this one here. Okay. So I'm correcting this one. You might need to help me here with the values. So this will give you what? Will give you then, this will be negative because we'll be in compression. So minus 12,900 divided by A, that I think we calculated, okay, over here. All these values were given over here on the previous pages. So let's say divided by 13.3518. We have that one over here. And because over here we did the moment is in the middle, what will be Z and X? I think we say will be 0. So we have this plus 0 plus 0. Okay, so this should give you what? Instead of 1,000, I'm guessing about 900 something.
966.
966. Okay, 0.16. PSI, you can decide to put the minus sign or no minus sign. Personally, I'd rather leave it that way and right on the side that we know that it will be in compression. Yes.
We had a zero for the X. There's IX and I.
Are we talking about the Z and X or the moment of inertia? So IX and IZ.
Are the same.
Correct. I think we calculate them. They will be the same. Yes. They are the same because it's a circle. Yeah, you're correct. Okay, and then we need to find the shear stress. Shear stresses. At point H. Okay, and we did one, I think. Yeah. So for example, in this case, we had the moment. I didn't put it here. That one here. Yeah, okay. On this one, you see I didn't put it. I'm going to do another figure here. I think here. So we took care of MX. And Z, but the one on the Y, which is My, which is really equal to the torque, in here was equal to 24,000. And I think I did this one clockwise because they say it's negative, okay? When I look over here. All right. So we have the result for that one, probably. Yeah, okay. So we can say here that, let's say tau sub 1, so due to torque, the expression is T sub R over J. So we had over here 24,000, and I think last time we added all these dimensions here. Yes. What was the units for the moments that we had over here? $24,000 is from here over here, okay? 24,000. In here I have, this is, yeah, so this is, the units were force per foot, no? Okay, so I think we already did that. Then we need to multiply this one by 12. Then R over here would be what? At the middle, what is the R upon H? 0, so we are over here divided by whatever this was. So this is going to give us that due to the torque, this is equal to 0. So again, like I told you, I did a mistake initially, or the mistake. In here, we calculate for H, but what would be if it was, if H, let's say, was over here? Then it would be, it would not be 0, no? Okay. All right, and the next thing, I guess, we need to find the shear stress. U2. So we have the forces over here, so let's do this one over here again. One. So we have the two forces that were we had a Vy over here equal to 12,100, and we had over here a Dz equal to 3,000. Okay, so the general equation for this is what? Tau equals dq over it. All right, so over here, I think that's where we stopped last time. What is the definition of Q?
It's first.
I mean, it's YDA, no? But what is the simplification we have? It is what? Usually we do, okay, Y bar or yeah, Y bar if you want times the area, no? Okay, so in this case, let's do first the area. What would be the area? The what?
Didn't we already calculate that earlier? Like 13.3.
Yeah.
We calculated the Q before?
No, just the area.
Oh, the area.
Yeah, we got cross section.
Okay, that's fine. So let's say is, but I want to put it here would be correct. So would be pi d square to the 4, no?
2 pi.
Correct. But let's say the general expression. All right, I'm just doing now general. This is the area, no? Okay, and now what would be resisting the, what would be the distance? The over 2. So we calculate this Q over here. I agree with you that we have that one would be what? Pi over 4 d outside square minus d inside square times the out. I mean, Johnny, you should take the average if you want. The out, if you want to do the out plus the inside divided by 2. And I'm not going to have a value for this one. So I have a value for the first part. So Q will be equal to, you agree this is 13.3518 times 1/2 of, okay, 9 plus 8. So what do you get for Q over here?
3 out over d plus the n over 4, because you're looking for a radius, right? Not a diameter.
Let's see. Yeah, we're looking. You're correct. So we'll be, yes, absolutely correct. So this one divided by 4. So just divide by 2. What is the value?
Q is equal to 56.74.
50.
56.745.
Okay, and let me put it, okay, be on the next page. And here, what would be the, and what should be the T? We're talking about that now. What should be the T?
That'd be the diameter.
So it would be the diameter because it would be half on each side, no? So it would be the D outside minus the D inside. Okay, it's that thickness over here. Okay, so now basically we can just go and substitute. No, we got all the values. All right, so let's say we're gonna have here tau sub 2 will be equal to the EZ over Q here they would be the same. It would be what? This should be what? IZT, and then tau sub 3 should be BXQ over IXT. So 1 will give 12,900 times 59.745 divided by what was over the i's. We found that to be equal to 121.004.
Should be 56.
50, oh, sorry. 6.745. And this should be basically 1, no? Yeah, 9 minus 8. And this one, I think, is the same thing, but with 3,000. Times 56.745. Divided by 121.004 times 1. So that's
House of 2, you said that V1 equals 12,900.
yes, I took it over here.
Yeah,
It should
so
be
the value doesn't match like the,
no, it should not be VY. VY was the one going down.
yeah, but that's the one.
It should be the VX. It was no VX. I don't know. You are correct. This one is the in plane, not the VY.
Yeah,
So it should not go doing shear. It should be the. So it's only VC.
yes,
Yes, it's only this. Correct. This is the in plane. So they said this one is there's no VY. Sorry for that. You're absolutely correct. So we can remove then this one here. Thank you. Yeah, and this one is split out. So let me just redo a page. So tau sub 2 will be equal to V Z Q divided by I sub ZD, which is 3,000 times 56.745 divided by 121.004 times 1. So what did you get for this one?
1,406.
1,400. 1,406.85. Yes. So basically, I mean, these problems, you see that you need to be careful because it's easy to do more mistakes. And the important thing is the figure. So this figure here, you see, I didn't do it properly. That's why I put the VY. I thought, and this one should be the in plane, no? Do you understand what happened here or not? Yeah. Do you understand what happened here, everybody? That VY was actually coming in, no? That way, it's on the in plane. It's not creating shear. Yeah. Okay, but because my figure was not good, that's why we figured the problem. All right. So, any question about the procedure over here? So let's do a summary. Correct. What happened? We threw out the VY because that one, because I didn't do properly the figure. So what happens is that the VY is really coming in the actual direction of this cross section. Okay. It's not coming tangential producing shear. So it's really producing the normal, which is the value that we put over here. Okay. Okay. All right. Yep. But that's because you see I didn't do a good figure. So I've done a better figure. One. Okay. So procedure. Let's see what we did. So the most difficult part is, I would say, is to find the loading. In order to define the loading, define position vectors. Which were basically the I, the forces, put it on the vector form. In vector form. And then you calculate the moments. By using the equation what? R cross F. All right. Then important. do a good sketch or figure. So in this case, I didn't do such a good job. Probably a bit better would be something to do like this. All right. In here, let's say here for forces. And here for moment. So you see we here would be the axial direction would be Y, X, and Z. Make sure you put the forces Fy, Fx, Fz. Then that you define the property, the moment. So you know this one really is My, but would be the torque. This will be bending. And this will be bending, no? Okay, I'm doing circular cross-section, that it can be any cross-section, okay? So this is the way I will do it. Step 2, I will go and let's say properties, cross-section. Okay, so I will calculate what? The area. I will calculate the moments of inertia. Okay, if it's non-symmetric, you might have something like this, no? And then we'll do what? Bending stresses. Which is the equation. So for us, the bending stress should be in what direction? Be on the axial, which is the Y, no, in this figure. And the equation we had for this one was, so let's say will be Fy over A. Then this one can give bending moment, will be mx times, let's say, Z divided by Ix plus mz times X divided by Iz. Remember over here what? Sine given by tension or compression. You need to understand what is happening, not in the structure. And then you calculate the shear stresses, that you have two types of shear stresses. First one is the ones due to torque, which is the easy equation, TR over J. And then there is the other ones would be the due to shear forces. So this time would be what? Tau equals dq over IT. So does all that make sense? Yeah. All right. So the important here is, it doesn't matter. I mean, I think this is the right way I will do it. But if you calculate first the properties, it's fine, no? Okay, before the loading. Okay, you change a bit the order. But I'm just trying to teach you a procedure that you can follow all the time to get a result. Okay, so now we are missing one more type of stresses. On the shear stresses, which is the one, for example, what are the stresses if you have, let's say, a tank, let's say you have a tank inside with oxygen. The inside pressure is going to also create stresses on the outside of the tank, no? All right. So that's the only stresses we are missing. So, and after that, okay. You have a question first. What's the question?
Oh, I don't know. I have to keep my arm like this.
No, behind you.
Oh, sorry.
Standard question can be on the test.
No, this is not part of the test. Okay, but basically, so those stresses I was just talking is cool, and then. So that's going to be probably the next lecture, and after that, which is really what is the important part for the design, is that generally when they give you the data from the books, okay, for your design, generally what do you get? They give you the allowable or the ultimate stresses, no, that the structures can resist. Okay, so in solid mechanics, I think you have seen it, but you know you can combine the bending stresses or the normal stresses with the shear stresses. You combine them together to find the principal stresses, no? Okay, so that's what will be coming in the coming weeks, and we see why they do that. So there's different approximation. One is to find the principal stresses. Other form of fine stresses is called the von Mises stresses. Okay, they have the Tresca stresses. They have different stress criteria for different design cases. Okay, so I'm going to stop this video and I will attach that one to the one next time.